Okay, I started with the record. And let's see what we have to do today. So today in our calendar, we have April 25th. So we have temperature and then thermal expansion of solid and liquids and heat capacity and specific heat. And all this week will be essentially about thermodynamics and is the last topic, the last big topic of this course. Okay, now let me share the slides. Stop share, where is it? Share again. Those are the slides that, as you know, will be uploaded in Laulima, and the videos recording will be uploaded in the YouTube channel. So let's see heat transfer and phase change. First of all, we need to define heat. Heat is a form of energy and therefore is measured in joules, as we have seen for the other energies. So there are several units, but the most common one is kilocalories. 1 kilocalorie is defined as the amount of heat needed to raise the temperature of 1 kilogram of water by 1 Celsius. And so 1 calorie is 0.001 kilocalorie, of course. Now here the figures illustrate the 3 most common units of the heat. So we have 1 kilocalorie, and we define it as here you have the heat necessary to increase the temperature of 1 kilogram of water of 1 degree Celsius, or you have calorie, 1 calorie, or we also have the British thermal unit, but we don't use it, this one. So if it is energy, how do calories convert to joules? This is important. And we have that 1 kilocalories is equal to 4,186 joules. Okay. And this is also an experiment that was used to be able to find this correspondence. So the specific heat instead is the amount of heat needed to increase the temperature of a solid or liquid that depends on the amount of the substance and the properties of the substance itself. So it makes difference if the substance, depending on the substance. And so we call Q, the amount of heat needed, is equal to C m delta T, where C is called the specific heat of the substance. And as we said, so delta T is the temperature, and then m is the amount of the substance, so the mass. So here, what we have a specific heat for all the different substances, some of the different substances. So we have solids, and you can see that the specific heat can be joule per kilogram per Celsius. And you know why? Because C, if we want to find C, is equal to Q divided by M delta T. So Q is in joule, M is in kilogram, and delta T, we just say that is in Celsius. So this is the units that we are used to have. Or we also say that instead of joules, we also use kilocalories. So everything at the denominator stays the same, but at the numerator, we have here kilocalories. So joules, kilogram per Celsius. And we see the different specific heats for various substances, considering 20 C and considering the pressure of 1 atmosphere. So you see, for example, aluminum is 920, and then let's see, a glass is 840. And then, for example, we have liquids, which is way bigger, you see, is 2,450, or for the gas, as a vapor of water, is about 2,000. And here you have the correspondence in kilocalories. So calorimetry is the quantitative measurement of the heat exchange, and is done using a calorimeter, which is insulated from the environment to be able to minimize the heat exchange. So the heat lost by one object in a calorimeter must be gained by another, okay? Because everything is insulated. So this is one way of measuring the specific heat. The specific heat can also be defined for gases as well, but gas do not have a constant volume or pressure. So we define two specific heats for gases. One, when we have a constant volume. So if we keep the gas inside the volume, which is constant, although it might change the pressure, but we have a specific heat, which is CV. And one with the constant pressure instead, when we keep the pressure constant, but what it might change instead is the volume. And we have what is CP. And for a particular gas, what we notice is that CP is always greater than CV. And so every subspecific heat, every substance requires a unique amount of energy per unit mass to change the temperature of that substance by 1 degree Celsius. And this is direct proportional to the mass. So the specific heat C is C divided by capital C divided by M. And we also seen that is Q M delta T. And the units, we see that before, in the international system is joules, kilogram, and Celsius, and in CGS is calorie, grams, and Celsius. Do you want to add anything in this part, Mike?
Yeah, thanks. Actually, I there's two things I'd like to add. Up above, you on one of the earlier slides, you mentioned kilocalories and regular calories. And I just wanted to remind everybody that kilocalories, or calories with a capital C, is what is the same thing as a dietary calorie. So it was, I'm sorry, I don't remember which slide, but it was one of the ones way back there. Okay, so here, this is actually, that one was good. If you go to slide 3. Okay.
Yeah.
So when you see a calorie with a capital C or a kilocalorie, this is the same thing as one dietary calorie. So when we talk about calories in our food, right, then that's what we're talking about. Whereas lowercase c calorie, people will often refer to that as a heat calorie, and it's 1,000 times smaller, right? Dietary calories are 1,000 times bigger. Yeah, they're kilocalories. I know a lot of you are already familiar with this because this is used heavily in chemistry class as well. So if you've already had Chem 161 and 162, then you've seen this before. And then my second comment was just when you look at the specific heat formula, yeah, slide 5 is great. Whenever you see a delta T, it's okay to use either Celsius, or Kelvin. Right? Because both of those, okay, so you can either use Celsius degrees or you can use Kelvins, because both of those are centigrade scales. Both of those have 100 degrees in between the freezing point of water and the boiling point of water. So if you take a delta between two temperatures in Celsius, it's the same as when you take that delta between two different temperatures in Kelvins. However, whenever you see a formula that has just a pure T in it without the delta, so an example of that is for the ideal gas law. You see P1 V1 over T1 is equal to P2 V2 over T2. This must be Kelvins. Okay. In other words, you have to use something that is based on an absolute zero scale. Okay. So delta, so in summary, when you see a delta T, you can use either Celsius or Kelvins, and it's the same answer. When you see just T by itself, an absolute temperature, it must be Kelvins based on an absolute zero scale. All right, thanks.
Very good. Very good. Okay. So heat, what is it? It's the flow of energy due to a temperature difference, and always flow from an object at high temperature to objects at low temperature, right? And when two objects have the same temperature, we say that they are in thermal equilibrium. So for example, even when you have your cup of coffee, because the cup of coffee is around the cup of coffee, there is air, right? There is air, then you have the table. So all the surfaces are in contact with something that it has a lower temperature. And because it has a lower temperature, then your cup of coffee, if you don't drink it fast enough, is going to get cold. It's going to get a room temperature. And this is, for example, a bit different in space, especially in deep space where there is no air, and so there is vacuum. If you have an object, one of the main challenges when you build the instrument for space is that you cannot really dissipate heat. So if you are using electronics, you see when you use your computer that it becomes hotter and hotter, right? The more you use it, the more it gets hot. And the thing is that while here we can dissipate because it's in contact with the air, in a space where there is vacuum, is not in contact with anything. So you need to find solutions, very smart solutions, to be able to dissipate the heat. Otherwise, it's going to get too hot. And when we said here that two objects have the same temperature, so there is no more exchange of heat because they have the same temperature, and then we get the thermal equilibrium. Mike, when you want to add something, just do it. Just, yeah, feel free.
Great, thanks, I will.
Okay, so if objects A, the zero law of thermodynamics, let's say, can be considered like if we have three objects here, and if objects A and B are separately in thermal equilibrium with the third object C, which means so that A is in thermal equilibrium with C, B is in thermal equilibrium with C, then A and B are also in thermal equilibrium with each other. Okay, it makes sense. And you have done this somehow in different fields like math, right? But it's the same principle. Then we have temperature scales. So the thermometers can be calibrated by placing them in thermal contact with an environment that remains a constant temperature. And the Celsius scale, the temperature of a nice water mixture is defined as 0 C, and this is the freezing point of water, while the temperature of a water steam mixture is defined as 100 degrees Celsius, and this is the boiling point of water. So for example, for me that I'm in Italy, we use the Celsius scale. One of the most challenging things was to get adapt to the temperature here, the temperature scale here, because for me, it was always easy to remember 0 is the freezing point. So if outside I see snow instead of rain, it means that we are below 0 or really close to 0. If I see rain instead, it means that we are way above 0. And then 100 degree, every time I make my tea, every time I make my pasta, I know how hot it is 100 degrees because it's the boiling point. And I know because unfortunately for myself, sometimes I drink my tea too fast or I touch the water to try to see if the salt is enough for the pasta. And so for me, it's very easy. The Celsius scale is way more different. Yeah, to understand the Fahrenheit scale for me is way more complex, but I'm getting better and better every day. So for the Fahrenheit scale, you don't need any instruction, you know way better than me. So it's the most common scale used in the US. The temperature of the freezing point is 32 degrees, and the temperature of the boiling point is 212. And you have 180 divisions between the points. This is, yeah, something for me very crazy, but it is what it is. I need to adapt to the new rules and challenge myself like everyone else. Then we have something that is even more complicated to understand, which is the Kelvin scale. So when the pressure of a gas goes to 0, its temperature is minus 273.15 Celsius. And this temperature is called absolute zero, so minus 273.15 Celsius. And this is the 0 point of the Kelvin scale. So to convert from Celsius to Kelvin, you need to always remove 273.15. Just to give you an idea, yeah, in CERN, because you need to have a very, very powerful magnets, and to have very powerful magnets, you need to use what is called superconductivity. So you need to bring the temperature to the zero absolute so that you don't have any more dissipation. So all these big coils are kept at this temperature to be able to have the superconductivity, and so to be able to create these huge magnets that are used to bend the particles. And like this, the particles are able to really, once you shoot them, they are really able to follow a path and collide in specific locations around which we make all a series of detectors to measure the constituent of matters. So the coolest point, I believe, in the universe is essentially this superconducting magnet that we know of in the universe, are these superconducting magnets that are making up for the accelerators, particle accelerators. Because yeah, as Mike is an astronomer, so he even knows better than me, also the CMB, cosmic microwave background radiation, has a higher temperature, right, Mike? Do you want to say?
Yeah, it's 2.7 kelvins. Yeah, the universe as a whole is mostly at 2.7 kelvins. That's right.
Yes. So the universe is 2.7 Kelvin. So it's not absolute zero. And it brings this CMB brings all the relic from the Big Bang. So very, very useful information about our universe. And yeah, so those are the two things that we know about the Kelvin scale in real life, let's say. Okay. So to give you also some representative Kelvin temperature, we can also see here, for example, where do we use the temperature in Kelvin? We use it, of course, in astronomy, we just said, with the CMB, but we also use it, for example, for the interior of the sun, is 10⁷ Kelvin, very, very hot. Hydrogen bomb, okay, 10⁸. Solar corona, so the atmosphere around the sun, 10⁶. The surface of the sun, we see that it decreases. And then here we have something from this planet. The copper melts at 10⁻³, and the water freezes sometimes here above 10⁻², and so on. And so here we have liquid nitrogen, liquid hydrogen, liquid helium, and this is the lowest temperature. So how we can compare temperature scale? We said if we have a Kelvin, if we have a Celsius, sorry, is important to just for the Kelvin is, and you know the Kelvin, is important that you take the temperature in Kelvin and you remove 273.15. So it's pretty straightforward. And of course, you can go also the other way around. So if you need to find Kelvin, you just sum 273.15. If instead you have Fahrenheit here, if you want to find Fahrenheit, then you have Celsius, you have to consider the temperature in Celsius, multiply by 9, divide by 5, add 32, and then you are going to find the temperature in Fahrenheit. So that's why I'm having these difficulties, because every time I need to make this calculation in my mind. And this one is also the delta T Fahrenheit is 9/5 delta T in Celsius. So when Mike before was speaking about delta T between Kelvin and Celsius, you can really use them.
Right.
Yeah,
they're the same.
they are the same. But if the temperature is in Fahrenheit, then you have to use this formula.
So could I just add one comment?
Of course.
Because there are 100 degrees between the freezing point of water and the boiling point of water, we often say that this is a centigrade scale. And I hope that everyone can see the origin of that word, right? Centi is 100. So there's 100 degrees between the freezing point and the boiling point of water. Kelvin is also a centigrade scale, right? Although when you hear people speak in everyday language, when they say centigrade, they often mean it as a synonym for Celsius, right? So they'll say, what's the temperature centigrade outside? But really, centigrade just means there's 100 degrees between the freezing and the boiling point of water. That's why the delta T is the same for Celsius and for kelvins. Whereas Fahrenheit is just crazy. It's 180 degrees between these two, right? So I don't know where that came from. It's a historical artifact. One very minor thing, notice that with kelvins, sometime in the mid 1900s, we stopped writing the little degree symbol. So for Kelvin temperatures, the little degree symbol is missing, whereas for Fahrenheit and Celsius, we use the little degree symbol. Don't know why, again, but just so you know, yeah, that's the current custom. Thanks.
Yeah, and just one thing that is just for out of your curiosity, centigrade derives from, for example, if you say this number 100 in Italian, 100 in Italian is cento. Cento, which is very similar to centigrade, right?
Right. And centimeters, there's 100 centimeters in a meter, right? So yeah, a centipede has 100 legs.
Yes, very good. So let's do an example. On a warm summer day, the air temperature is 84 Fahrenheit. Express this temperature in Celsius and then in kelvins. So here we have to apply the same expression of before. So 84 Fahrenheit, here 9 divided by 5 is 1.8. So temperature in Fahrenheit is 1.8 Fahrenheit over Celsius, temperature in Celsius plus 32 Fahrenheit. And so you just apply this number and the T in Celsius, so is equal to T in Fahrenheit, temperature in Fahrenheit minus 32. So we need to do 84 minus 32 divided by 1.8. And it comes out, now I don't know out of my mind, I should put here the result. How much it will be? 84 minus 32 divided by 1.8. I should do it like this. I've been doing it so many times now. But I have to say, I have to admit, I use my phone every time. So 52 degrees Celsius. Yes, 52 Celsius divided 1.8, which makes 28.9 degrees. Yes. You can imagine that in Rome in the summer, we get even to 42 degrees. So 28 is a warm summer day. Very good. It's like essentially similar to what we have right now, right? Then we have absolute Celsius instead, which is T is equal to T in plus 200 in centigrade plus 273.15. So we just do 29 or 28.9 at this point, 28.9 plus 273.15. And here we are. Okay, 302 Kelvin, which is about 302. Perfect. Thank you so much, Mike.
My pleasure.
Okay, so then we need to define the state of matters. You probably already know these things, but let's see them very quickly, and then we do some example. We have three phases of matter: solid, liquid, and gas. Solid has a defined shape and the strongest intermolecular bonds. Then we have liquid that flows, but is relatively incompressible, and it has a definite volume. And the gas is compressible and will expand to fill completely a container. So he has the solid, we said he has defined volume, defined shape, and the molecules are at in specific location by electrical forces and vibrate about the equilibrium position, and can be modeled here, as you see, as springs that are connecting all the molecules. Instead, for the liquid, we have a definite volume, but it doesn't have a definite shape, and they exist at a higher temperature with respect to the solids, and the molecules wander through the liquid in a random fashion. So they move from one place to another, and then the intermolecular forces are not strong enough to keep the molecules in a fixed position. And here you have also the collisions. Since we did the collisions some time ago, so we have the collisions of the molecules inside the container that keeps them. And then we have the gas, where the collisions occur even more, that has no definite volume, no definite shape, are in constant random motion, and they exert only weak forces on each other, and the average distance between molecules is large compared to the size of the molecules. And then we have another form of matter, which is plasma, which is a matter heated to a very high temperature, where many of the electrons are free from the nucleus. And this results in a collection of free electrically charged ions. So you have a nucleus on their own and electrons that are going on their own, because the temperature is so high that they are free to go wherever they want. So a phase change occurs when the physical characteristics of a substance change from one to another. Common phase changes are from solid to liquid, melting, like melting ice cream when it becomes liquid, from liquid to gas, boiling, like our boiling water. And phase change involves a change in the internal energy, but not a change in the temperature. So when you get to the boiling point of water, the water keeps moving from being liquid to being a gas. And if you keep it for too long, you will see that you end up with no water whatsoever. But during that time, during that entire change, the phase change, the temperature is still 100 degrees. So it doesn't change. What you have is a change in the internal energy, but not in temperature. So how do we call this phase change? As we say, solid to liquid, we said melting. Liquid to gas, we said evaporating or boiling. Gas to liquid, we said condensing, which is what we have, for example, in the windows when you have air conditioning inside and outside is colder. Liquid to solid, we have freezing. And solid to gas, which is something that occurs more rarely, is sublimating. Latent heat is the amount of heat that is absorbed or released when a substance undergoes a phase transition. So latent heat is the amount of heat that absorbed or released when a substance undergoes all this phase transition, okay? And here we give you the definition. So during a phase change, the amount of heat is given by QML. So it's no more C, the specific heat delta T, because we have seen that during a phase change, delta T is equal to 0. We said before, there is no change in temperature. But what it changed is anyway the energy. So we have an amount of heat that is exchanged, and we have that depends on the mass and depends on this L, which is called latent heat of the substance, and is the amount of heat per unit mass required to change the phase of a substance. The energy is used to form or break chemical bonds. Latent means indeed hidden or concealed. So we need to choose a positive sign if you're adding energy to the system and a negative sign if the energy instead is being removed from the system. And for example, here we have, we are going to call latent heat of fusion L with a small f when we are melting or freezing, and latent heat of vaporization with a small v, LV, is used instead for boiling or condensing. And here we have some of these latent heat values for the melting or for the boiling point. For example, let's see, water, the melting point of freezing point is 0, and the boiling point of vaporization point is 100 degrees. And then you might see, for example, for oxygen, the melting point is 219 C. And this is really good because it will be impossible to breathe cubes of oxygen, right? If it will be 100, if it will be 0 C like for the water. And here you have for oxygen that is the boiling point is minus 83 Celsius, for example. And then here we have alcohol, so it's minus 114 Celsius, and the boiling point is 78 C. Mike, do you want to add anything?
Yeah, actually, I'll just add two things. There's, unfortunately, this list is in alphabetical order, which is not too helpful. But if we could put it in order of atomic weight, one of the things you'd notice is that the melting temperature and the boiling temperature gradually increase with the atomic mass of the substance. So this is melting point theory and boiling point theory, and it would also increase with the strength of the interatomic or intermolecular bonds that exist in that substance, right? So if the molecules or atoms of a substance are held together only weakly with like van der Waals forces or whatever, then it'll have a relatively low melting point and boiling point. But if they're held together strongly by, let's say, ionic bonds or covalent bonds or some combination of those, then it'll have a relatively high melting point and high boiling point. The second thing I want to point out is water is pretty special. If you look down this list here of latent heats of fusion or latent heats of vaporization, water has one of the very highest of the latent heat of fusion, which is going from ice to liquid, right? Or liquid back to ice. It's huge. It's enormous. And on even the latent heat of vaporization, it's one of the very biggest on the list as well, right? I mean, I don't know about tungsten, but if you ignore the tungsten, then water basically takes the prize, right? So this has lots of implications for life on Earth. Both of those things do. And so I'm sure that's already been discussed in your chemistry class and biology class and so on. But this is well known about water, that it takes a lot of energy per gram or per kilogram of water to boil it or to melt it, and again to boil it. So H2O can be a real reservoir for absorbing heat, but also for storing heat as a result, compared to most other substances. Thanks.
Very good. So here, let's look at 1 second at these phase changes and latent heat. What we have, for example, now is pretty small. I don't know if you can see it well. Let me maybe.
Oh, I'm sorry, Dr. Bendy, could I just add one last comment about the thing I was
Yes.
saying about water? Go leave this slide up, that's fine. The reason water has this very strong latent heat and very strong, latent heat of fusion, latent heat vaporization is the strong polar bonds that exist between the water molecules. That's why, right? It's one of the most polar substances. And as a result, the water molecules like to stick together much more than other substances do when they're near each other. Thanks.
Very good. So let's see some phase change. For example, here you see that we have a temperature. So in the number 1, we see that we have a highs. So we are below 0. And then in the x-axis, you see that we have heat. And in the y-axis, we see that we have temperature. If we increase a bit the temperature, means that we are providing heat, so means that we are warming the ice. We get to the temperature 0. When we get to the temperature 0, if you see in number 2, you see that we are increasing the heat, so we are providing heat to the system, but the temperature of the system stays the same. And in this case, we have that we are melting the ice, and we are melting the ice, okay, until we finish melting the ice. And after that, if you go to number 3, if you keep providing heat to the system, what you're going to have that after the ice is all melted, the temperature of what now we call water, because we are not going to have any more ice, is going to increase. It's going to increase. The more we add the heat, the more the temperature is going to increase. And this is going to go on, as you see, number 3. And in number 4, is going to arrive to a temperature which is 100 degrees. And when the temperature of the water is 100 degrees, we know that it starts to vaporizing. So it starts to boil the water. And again, if we keep providing heat, the temperature will stay constant during that period of time. And will stay constant because it's going to, all the water is going to vaporize. And then in the last part, if we keep providing heat to the system, we are going at that point to have all steam, okay? So while before is going to be water and steam, then once we finish heating evaporating all the water, we only have steam. And if we keep providing heat to the system will increase in temperature again. So here, if we want to see all the heat provided to the system, we need to add all the heat that has been provided for each of these phases. Okay, so Q total is Q1 plus Q2 plus Q3 plus Q4 plus Q5. And you know how to find Q in each one of these situations. So here you are going to use this formula. Let me show you the formula that we saw before. This one, MC delta T. While when we are in this phase here, melting ice, where there is, in this case, melting ice, vaporizing water, you will have to use instead this other formula. With LT is going to be LF when you are melting and LV when you are vaporizing the water. We will see some example with this. Do you want to say something, Mike?
No, it's okay. I think we'll just wait for the example. Thanks.
Okay, so you need to use consistent unit. So transfer in energy as given as Q is MC delta T for processes with no phase changes. And you have to use Q equal to MLF or Q equal to MLV if there is a phase change. And then in Q cold is you are decreasing the Q, so is negative, while normally when you add heat, if it's hot, is positive because you are adding heat. And so you need to be careful to the sign because delta T is always T final minus T initial, as you remember, as we always did. I want to show you as a last thing before doing the problems. On a phase diagram, we have what is called the tripole point, that is the set of the P, the pressure, and the temperature, where all the three cases can coexist in equilibrium. For example, here we see we have a certain temperature, and here we have a certain pressure. And so in this case, we have a vapor. In this case, we have solid when we have a lowest temperature and high pressure. In this case, we have a liquid, and here is shown all the change of state. from solid to liquid to vapor, and this is called instead triple point, which is these three phases can coexist in equilibrium.
This looks like the diagram for water, right? For H2O.
Yes.
Great. Could I just add one comment? And that is water has this really peculiar property that some of the liquid forms of water can be denser than the solid form of water, meaning ice can be less dense than liquid and ice floats. That is not true for most substances on Earth. There are a few, but that is not true. So that's why this shape of the phase diagram curves backward for water, but it turns out that that particular line for most substances will curve the other way. It'll curve this way. So for most substances, the phase diagram will have a shape more like that. So, but water is kind of special. You can have solid water here, and then as you increase the pressure and crush it harder and harder, it'll actually turn back into a liquid, which we think is what happens on at the bottoms of glaciers, right? The ice is under so much tremendous pressure that it actually like reliquefies. But that's rare. Usually if you have a solid and you put under more pressure, it stays a solid. Thanks.
Okay, so Q is equal to MC delta T. Delta T is always the final temperature minus the initial temperature. When the temperature increases, delta T and delta Q are considered to be positive and the energy flows into the system. When the temperature decreases, delta T and delta Q are considered to be negative and the energy flows out of the system. This is the convention that we use. So let's see an example. How much heat is needed to raise the temperature of aluminum by 5 degrees Celsius? So here is provided the mass of 0.5 kilogram. The temperature delta T we said is 5 degrees Celsius. The specific heat of aluminum is 900 joules kilogram per Celsius. So what we have, we use Q is equal to MC of aluminum delta T. So 0.5 kilogram, 900 joules divided by kilogram per Celsius. And here delta T is positive 5 degrees Celsius. So we need to provide to the system 2,250 joules. Okay. Then let's see another example. We have a 0.400 kilogram aluminum tea kettle that contains 2 kilograms of water at 15 degrees Celsius. How much heat is required to raise the temperature of water and kettle to 100 degrees Celsius? So the heat needed to raise the temperature of the water is Q of the water is equal to the mass of the water, specific heat of the water, delta T. And so we have 2 kilograms of water. This is 4,186 is the specific heat of water. 85 degrees because the water was 15 and now it needs to get to 100. So 100 minus 15 is 85. So if I do the calculation, I found that is 1712 kilojoules. While the heat needed to raise the temperature of the aluminum is here we have mass of the aluminum, C of the aluminum, delta T of the aluminum. So here the mass of the kettle is 0.4 kilogram. Then this is the specific heat for the aluminum. 85 is the delta T, the same delta T, 100 minus 15. If we do the calculation, we find 30.6 kilojoule. So the total heat that you need to provide to the system is provided by the heat that you need to provide to the water to be able to make the water boiling, but also the one that you need to provide to make the kettle at the same temperature of the boiling water. And so Q of the water plus Q of the aluminum. And so you sum up these two numbers, and this is what you find. Tell me if you have questions or anything. Now we have a 0.01 kilogram piece of a known metal, which is heated at 200 degrees Celsius and dropped into a bucket containing 0.5 kilogram of water at 20 C. Okay, so we have this amount of a unknown metal, 100 degrees Celsius, that is dropped into a bucket of water that contains this amount of water at 20 Celsius. Determine the specific heat of metal if the final temperature of the system is 50 Celsius. So the mass of the first object, the unknown metal, is 0.01 kilogram. The mass of the water is 0.5 kilogram. Then we have the specific heat of the water, which is something that we know. Then what do we know? We know that the temperature of the metal is 100 Celsius. The temperature of the water is 20 C, and the final temperature is 50 C. So we need to know that for the conservation of energy, the heat that is lost by a metal is the same as the heat that we are going to acquire into the water. So Q water plus Q of the metal is going to be equal to 0, because all the heat that the metal lose is going to be gained by the water. So 0 is going to be equal to mass of the metal, C of the metal, delta T of the metal, plus mass of the water, C of the water, delta T of the water. So the mass of the metal is 0.01 kilogram. C of the metal is what we are looking for, so we don't know. Then we have the difference of temperature. So the initial temperature, the final temperature is 50. It says that the final temperature of the system is 50 minus the initial temperature of the metal, sorry, was 100 Celsius. Okay, here we are good. Plus, what we have all the information coming from water. Water is mass of the water is 0.5 kilogram. This is the coefficient for water. And then what we have, final temperature 50 degrees Celsius minus initial one, which was 20 Celsius. Okay. If we make all the calculation, we find minus 0.5 Celsius of C of the metal, which is what we are looking for, plus this amount of joules is equal to 0. And so we can find C of the metal and identify from the label from the table of before that the metal is iron. So here the difficult part, if you want, was to identify the fact that the heat that is lost by the metal is gained by the water. So at the end of the day, the exchange of here, the sum of this heat, because one is plus and one is negative, is going to be equal to 0. Let's see one that involves instead the change. It's really the last minutes when we are doing this interesting example. So we have a 75-gram cube of ice at minus 10 Celsius, which is placed in 0.5 kilogram of water at 50 degrees Celsius in an insulating container so that no heat is lost to the environment. Will the ice melt completely? What will be the final temperature of the system? So let's see. Here, what is the heat required to completely melt the ice? Q of the ice will be the mass of the ice, the C of the ice, delta T of the ice. Okay. Plus, here we have a change. So we have the mass of the ice and LF, because it's melting and fusion, right? So the mass of the ice is 0.75 grams. So it's 0.75 kilograms. We need to change from grams to kilograms. Then we have C of the ice. The C of the ice is 2.1 kilojoule divided by kilogram Celsius. And this you can get it from the table. that we see before, and then multiply by 10 Celsius. Why 10 Celsius? Because in this case will be final temperature, which is 0, minus initial temperature, which is minus 10. Minus 10 brings plus 10. Okay. And then we have the mass of the ice, again, 0.75 kilograms. What if it all melts in water? So the L of fusion is 333.7 kilojoules per kilogram. So if you do all this calculation, you find that the heat required to completely melt the ice is 27 kilojoules. And then what will be the final temperature of the system? So the heat required to cool the water to the freezing point instead, because we have this cube of ice placed in this amount of water. So the Q of the water is mass of the water, C of the water, delta T. The mass of the water is 0.5 kilograms. C of the water is this amount here. Delta T is from 50 to go to the freezing point, which is 0. So 50 minus 0 is 50 C, and it brings 105 kilojoules. So we see that here we have to melt all the ice, I need 27 kilojoules, while to freeze all the water, I need 105 kilojoules. So since Q of the ice is slower than Q of the water, the ice will completely melt. Does it make sense to you? I hope it does. And if you ask what will be the final temperature of the system, to find the final temperature of the system, note that there is no heat lost to the environment. So the heat that gets lost by the water is gained by the ice. So 0, because we don't have any exchange of heat with the external system, is going to be Q of the ice plus Q of the water. So Q of the ice is going to be the mass of the ice, C of the ice, delta T, plus the mass of the ice, LF, which is exactly what we did before. And here we have the mass of the ice, C of the water, T final minus T of the ice, because we need to find the final temperature. What is this? So this one is the mass of the ice that will go to a certain temperature. So it's going to be like this one, but once has been melted. Once has been melted, what is going to be the final temperature? So mass of the ice, C of the water. So while here C was the ice, and now we have the C of the water, but the mass of the ice, T final, because the ice has been melted, T final minus T of the ice, temperature of the ice. Plus here what we are going to have, the mass of the water, C of the water, T final minus T water. So if we do all the calculations here, we are going to find that the T final is going to be 32.4 Celsius. And I'm sorry that we got to this at the very last minute. Here we have another example, which is simpler. So I'm pretty sure you can understand it by yourself. Right, because it's a bit late. It's a more standard problem. So more similar probably to what you will find in your exam. Are there any comments or anything?
No, doesn't look like it.
Okay.
Great.
Very good. Okay, so see you on Friday, and I'm going to post all these things online.